In this video, we'll talk about linear inequalities and interval notation. What is a linear inequality? Well, linear inequality is any inequality that can be eventually written in the form ax plus b, either bigger than 0 or bigger equal than 0 or smaller than 0, smaller equal than 0, or even not equal to 0. So no matter how complicated an inequality we may have, after simplifying, after releasing brackets and collecting like terms, putting everything to one side, we should be able to obtain a linear polynomial ax plus b and then compare it to 0. Here are some examples of simple linear inequalities. X is larger than 2. 2x is larger or equal than 6. X plus 1 is smaller than 4. As you see, all of these three inequalities, they are not exactly written in one of those listed above forms. However, it's easy to bring them to this form. For example, here it's enough to bring the 4 to the left and combine with 1. Over there, bring the 6 to the left. And the same in the first inequality, bring the 2 to the left. So according to definition, we can easily show that yes, those are linear inequalities. Here we have another example. This inequality is already given in a form as above. That's exactly this form. And finally, x different than 1. It's easy to see that it can be written in that form. Okay, but how do we recognize that an inequality is linear without doing those little steps to bring the inequality to one of those listed forms? Well, the simplest thing is to look at the power of x. If the power of x is just 1, then an inequality is linear. Okay, so what does it mean to solve an inequality? Well, similarly as for equations, we're looking for x values that will satisfy the inequality. So to solve inequality means to find all x values satisfying the inequality. This set of such values is called the solution set. So for instance, in this first example, any number that is actually larger than 2 will be among the solutions. So 2.1, 2.4, 38.5, 1,000 will be fine, because those numbers are really larger than 2. However, if x is equal to 2, well, this wouldn't be a solution, because we would have 2 larger than 2. That doesn't work. 2 is equal to 2, it's not larger than 2. So number 2 would not belong to the solution set. In the second example, to solve it for x, we would like to divide both sides by 2. So we are looking for all x's that will be larger or equal than 3. Any number that is larger or equal than 3 will belong to the solution set. In the next example, if we bring the 1 to the other side, we really have inequality x smaller than 3. So any number that is smaller than 3 but not 3 would be a solution. Let's look at the next example. To solve for x, we would have to do two steps. First, add 3 to the other side, so we'll get 3/2 x smaller equal 3. And the next step will be multiplying by a reciprocal of this leading coefficient. So if I would multiply on this side by 2/3 and on that side by 2/3, this reciprocal is chosen for the sake of cancelling the 3/2. So these two numbers will be gone and we end up with just x. That was our goal. And here the 3 will be reduced, so x is smaller equal than 2. This time x value 2 will be a solution to this inequality. Finally, the last example tells us any number that is different than 1 will be a solution. So we have all real numbers except for 1 among the solutions. Notice that the solution set for all those examples contains infinitely many solutions. So it's not like for equation that we usually expect exactly one solution. When we solve inequalities, we usually expect infinitely many solutions. And because of that, we need to come up with a good way of recording the solution set. We can't list all the solutions because it's so many of them. However, we can graph the solution set and also state the solution set in interval notation. For example, If we want to represent numbers that are bigger or equal than 0, but at the same time smaller than 4, we can draw the set by connecting the extreme points, which in this case is 0 and 4, but we also need to watch the endpoints and indicate if the particular endpoint will be taken or not. If the endpoint is taken as a solution, we filled in the last point of the segment, and if the point does not belong to the solution set, we leave the endpoint of the segment hollow. So that's an open dot, that's covered dot. The interval that this diagram represents will be written in the following form. For the covered dot, we use square bracket. For the hollow dot, we use round bracket. And then we list the extreme points in increasing order. So the starting point of our segment is 0, then we write a comma, and the last point of our segment is 4. Even though 4 is not taken, we still need to indicate it. We can't say, for example, 3.9, because there is still infinitely many points between 3.9 and 4. Even if you will try to say, okay, 3.999, there is still infinitely many points between this number and 4, so we are not trying to reach the last number of this solution set, because there isn't any. However, we are listing the endpoint of the segment, and the fact that this endpoint is not taken is recorded by using round bracket. Let's try some examples. Here we see a table with 4 columns. We are listing inequality, the graph that corresponds to the solution set of this inequality, and then 2 ways of recording the solution set. In this column we have set builder notation, and the last column is about interval notation. So let's look at the first line. 2x bigger equals 6. This is inequality that we already have seen on the previous slide. We solve it by dividing by 2, so x would be bigger equal 3. Therefore, any point that is larger or equal than 3 will be among the solutions. That's why we mark the extreme point, which is 3, and then put the arrow to the right, indicating that anything that is larger than 3 can be taken as a solution. The corresponding set builder notation is very similar to just the original inequality, except that we use the braces that signify the fact that we're talking about a set. So we have a set of all real numbers such that our numbers are larger or equal than 3. And we can visualize those numbers by using the arrow on the graph. Quite often we'll be asked to leave the answer in interval notation, just because this is a very concise way of recording a segment of points. And also interval notation is very visual. It is really one step from the graph. In this case, what we do, we list the first important point, the extreme point, and the last one. Well, we don't have the last one, so what we do, we use infinity sign. Since there is no last point, the bracket that we use for infinity will always be round. The bottom extreme point, which is 3, is taken as a solution because we had equation. So equal sign corresponds to the covered dot and corresponds to a square bracket. So that's our interval from 3 to infinity. Okay, let's fill up the second line. We do have inequality given here. First, let's solve this inequality for x. It's nearly x, but not quite, because we have a minus. So to get rid of this minus, formally, we multiply inequality by a -1. That causes that this minus will disappear and we'll have just x. But it also causes that the inequality sign will be reversed. Remember, anytime we multiply by a negative number, we reverse the inequality sign. And then 1 times -1 becomes -1. So practically, what does it mean is we're changing all signs, including the inequality sign. Okay, so the solution set is all x's that are smaller than -1. Therefore, -1 is the important point that we need to mark on the number line. And then we need to graph all the numbers that are lower than -1. That means arrow to the left. Notice that we have a hollow dot on the endpoint just because -1 is not a solution. It must be something smaller than that, not equal. Okay, how do we write set builder notation for the solution set? Well, it's a set of all real numbers such that, and we just restate the inequality in a solved form. So x smaller than -1, complete the braces. When we write the solution set in interval notation, we're looking for the two extreme points, including infinity or negative infinity, and we're looking for them starting from the left and proceeding towards the right, never the other way around. So from the left to the right, like order on the number line. Okay, so the first important point is actually negative infinity. As I said before, this is not really a point, but it's a concept. We start from as far as possible to the left, and we are going until -1. So round bracket for negative infinity, comma, until -1, and again round bracket because we're not taking the endpoint. One more remark. If we need to indicate positive infinity, we don't need to actually write the plus. It is assumed that if we don't write any sign, the infinity is positive. But if we want to indicate negative infinity, the negative needs to be written here. For both positive and negative infinities, we always use round bracket because there is no last point. Okay, let's look at the next example. This time we have just a diagram given. So let's read what's there. We have given all numbers that are actually larger than 5 because we have hollow circle here. So starting from 5, anything that is higher than 5. So the corresponding inequality would be x is just larger than 5. The set builder notation is nearly the same as this inequality. We just put the extra bracket, all real numbers x, such that x is bigger than 5. However, interval, well, let's start from the left. Oh, the first important point is 5, so I need to start with 5. What kind of bracket? Hollow circle means no endpoint, means round bracket. Comma, and I can go until infinity. Positive infinity, round bracket. Okay, what do we have given in the next line? Just interval notation. Maybe let's graph this so we can see the solution set from -infinity until -4. So -4 is important point. Let's mark it, for example, here. And -4 is with square bracket. That means this point is taken as a solution. Aside of this point, we need to mark anything that is lower than -4 to the left of -4 with an arrow like this. That's our graph. Okay, so now we see that this is a solution set to the inequality x is lower or equal because of this filled in dot. Lower or equal means smaller equal -4. So that's our inequality. Finally, the set builder notation is just this inequality packed in a set builder notation format. So all real numbers such that x is smaller equal -4. That's a solution set. Okay, what do we have in the next example? That's interesting. X bigger equal x. If I will subtract this x to the left, I really have 0 bigger equal 0. What are the solutions for this kind of inequality? What value x can have to make this inequality true? Well, if you notice, 0 is always equal to 0, so it's part of this inequality. So that statement is always true. No matter what is the value of x, this will always be true, which means the solution set is actually all real numbers, entire number line, everything. So we don't need to worry here. In a set builder notation, there's not much to write. We can just write the double braced capital R to indicate entire number line. In interval notation, we can say from -infinity until infinity. That also indicates entire number line. In the last example, this time the set builder notation was given. This is a set of all real numbers such that our number is different than 3. So only 3 has to be taken out of the solution set. Everything else is fine. So this time we actually have 2 intervals, because notice that an interval corresponds to a segment if we extend the meaning of segment to an infinite segment as well. So it could be an actual segment, or could be half a line, or could be a line. But in this case, we actually have 2 segments. Because of this missing 3, the entire number line is broken in 2 pieces. Therefore, in order to use interval notation in this case, following the rules, we need to start from the left-hand side first. So we start from minus infinity and go until 3. The 3 has to be skipped, no endpoint. But then we have another interval from 3 until infinity, somewhere here. Okay, round bracket as well. Okay, so we have 2 intervals, but they don't exist separately. We actually need to state that both of them together represent the solution set. To indicate this fact that we are taking them together, we use such a U. This U stands for union. We'll talk about the union in the next video. Okay, we have one more box to fill in, but this one should be easy. We just take whatever is written in the set builder notation. So our inequality is x different than 3. One more thing for review. I mentioned this in that point already, but let's reinforce that. When we multiply or divide by a negative number, we always reverse the inequality sign. So multiplying or dividing by a negative number causes reversing signs for all terms, including inequality sign. Other than that, we solve the inequalities the same way as equations. So let's try to solve some inequalities. In the first one, what we need to do is release the bracket. So let's multiply by 2. 12 minus 2x smaller than 6x plus 1. Then we need to collect terms with x on one side of the inequality. In this example, I will suggest to collect all the x's on the right-hand side, just because this will give us a positive coefficient by the x. So 6x plus 2x is 8x. Copy the inequality and bring the 1 to the left side. So 12 minus 1 will be 11. Formally, what we've done here is we added 2x, and at the same time we subtracted 1 from both sides of the equation. Finally, to leave the x by itself, we need to get rid of this coefficient 8. So we are dividing by 8. Therefore, x is larger than 11 over 8. Notice that if I would move all the x's to the left-hand side, let's try it on the side, I would end up with negative 2x, negative 6x, smaller than, and keep the 1 and move the 12 to the right, it would be altogether negative 8x smaller than negative 11. Now, at that point, I would like to divide both sides of inequality by negative 8. So divide by a negative number. That's a moment when we need to remember to reverse the inequality sign. So we'll end up with x bigger than negative 11 over negative 8. It's the same as before, 11/8. So yes, we could keep the x on the left-hand side as we used to, but then when dividing by a negative coefficient, we need to remember to switch the inequality sign. Since it doesn't matter if we do it this way or that way, if we notice that moving x's to the right will give us a positive coefficient, this way seems to be easier. So I'm going to erase the other way to make it nice and clean. Okay, we did solve the inequality. The solutions are all numbers that are larger than 11/8. What we need to do is to graph the solution set. Let's take a number line and mark the important point, and mark this important point 11/8. Since we don't have equation involved, the point 11/8 will be marked by a hollow circle. And then all x's that are above this point are the solutions. So that's the solution set. To give the answer in interval notation, we can state that the solution set is the interval from 11/8 till infinity, round bracket on both sides. Okay, let's try the second example. Here we can notice that the inequality is a bit more complicated, mostly because of those fractional coefficients. So let's get rid of fractions first. Normally, to clear fractions, we would multiply by lowest common denominator of 3 and 4. But let's observe a little bit closer. Do we actually need to take care of 4? If we distribute this 1/4 into the bracket, notice that both 12 and 8 are divisible by 4, so the 4 will be cancelled anyway. Therefore, we don't need to worry about the 4. The only thing that we need to worry is 3. Let's multiply the whole inequality by 3, and in the meantime distribute the 1/4 to the bracket. So we need to multiply each term, this one, and that one, by 3. Therefore, let's record this little 3 in the top in the numerator so we won't forget, and then we can calculate. The 3 cancels this 3, so we really have only the bracket, and the bracket doesn't need to be written anymore. Then it's minus 3 times 6, which is 18. Then we have negative 3/4 times the bracket. So for now, let's write it nice and slow. Negative 3/4 times 12x. The 12 goes into numerator, so we can reduce 12 and 4 in the next line. And then negative times negative is positive, and again 3/4 times 8. Now, since 4 reduces to 12, leaving us with 3, and here leaving us with 2, we can rewrite this inequality simplifying a little bit more. 5 minus 18 can be performed, that's negative 13. And here we have negative 3 times 3 is negative 9x, plus 3 times 2 is 6. Okay, next step will be to bring all the x terms to the left side. So we copy the 2x, bring the negative x to the left, it becomes positive 9x, and then we have bigger equal. Let's copy the 6 and bring the 13, it becomes positive 13. Altogether we have 11x bigger equal 19, and then we can divide by the leading coefficient 11, so we obtain x bigger equal 19/11. Now to visualize this set, let's draw a number line, and we'll place this 19/11 covered dot, filled in dot, to indicate that the 19/11 is included in the solution set, and everything that goes above 19/11. Therefore, our answer in interval notation is everything from 19/11, including the 19/11, until infinity, round bracket. Okay, so those were single inequalities that we solve the same way as regular linear equations. If we need to clear fractions, we do it either by multiplication if the coefficient in the bracket are divisible by the denominator, or by multiplying by LCD. The only difference between solving equations and inequalities is when we need to divide by a negative number. So in this case, I avoid the situation of division by a negative number, but I also showed you before what to do if we end up with a negative coefficient by the x. Then we have to switch inequality sign. Okay, but what if we have two inequalities that needs to be satisfied at the same time? Such inequalities are called simultaneous inequalities. For example, if I want to convey the message that I have in mind all numbers that are in between 2 and 3, I may write the inequalities as follows. My number x is larger than 2 but at the same time smaller than 3. This notation is very close to the picture that we can see on the number line. If 2 is, for example, here and 3 is over there, the x value can be anything that is in between, the entire segment between 2 and 3. Notice that these two inequalities, when treated separately, they need to be connected by the word and. That means that both of them need to be satisfied in order to describe the same interval. So those two simultaneous inequalities, as long as the x is exactly the same, can be moved together and written in one stream of signs, like this. To solve such simultaneous inequalities, we apply the same type of operations as if we would solve just regular inequalities, for example, adding or subtracting to both sides the same quantity, or multiplying or dividing both sides of inequality by the same value, except that if the value is negative, we switch the inequality. Now we do exactly the same, but we apply those operations to all three parts of this inequality at the same time. So, for example, how would we solve these simultaneous inequalities? We would formally subtract 1 from all three sides. 2 minus 1 is 1, x plus 1 minus 1 is just x, 3 minus 1 is 2, and then keep the inequalities the same way. Therefore, the solution to this problem is all numbers between 1 and 2. In interval notation, it will be 1, 2, round brackets on both sides. So this is a solution set. We can also state the answer by using the notation my x can be any element from this interval. So that's another way of presenting your solution. Okay, let's apply our strategy. We have simultaneous inequalities. We have three sides. We are after the x. So to get closer to x, what we're supposed to do is to get rid of 1. Subtract 1 from all three sides. That gives us 1 smaller equal negative 3x, because this 1 will be gone, smaller 5 minus 1 is 4. Now what we need to do is to get rid of this negative 3, which means undo the multiplication by a negative number. Red alert. As soon as we divide by a negative number, we have to switch inequality sign. In this case, in both places. So here we have bigger equal and over there bigger. Okay, let's finish the question. 1 divided by negative 3 is negative 1/3. Here the negative 3 will be gone, so it's just x, and that's what we wished for. And 4 divided by negative 3, negative 4/3. Which means that if x is a solution, it must oscillate between the number negative 4/3 and negative 1/3. We may want to record this on the number line. Let's say this could be negative 4/3 and that one negative 1/3, which is higher than negative 4/3. And x oscillates anywhere in between these 2 points. So that's our solution set. We can give the answer in interval notation. X can be any number from interval negative 4/3 until negative 1/3, half open, half closed interval. Okay, let's try another example. Here, to get closer to x, we need to get rid of this 4 first. So let's multiply all three sides by 4. We'll get negative 4 smaller, and this 4 will be cancelled, so we have just 2x plus 5. Smaller equal 3 times 4 is 12. And now we have very similar question to the previous one. We need to get rid of 5, so subtract 5 from all three sides. We get negative 9 smaller than 2x, smaller equal 7. And finally, divide by the leading coefficient 2. So the x by itself will oscillate between negative 9/2 and 7/2. Again, we can draw the number line, and the solution set is from negative 9/2 till 7/2, everything what's in between. Therefore, the final answer in interval notation will be from negative 9/2 till 7/2 inclusive. Similarly as before, half open, half closed interval. In the next exercise, we are asked to translate the sentence into inequality or inequalities and then solve it. Double a number increased by 1 is between 2 and 8. The phrase "is between" suggests that I'm supposed to have some sort of expression that will be enclosed by 2 and 8. Remember, between doesn't allow for the endpoint, so we don't have the equal sign here. It's strictly between. What is this expression? Double a number increased by 1. Double a number, unknown number, call it x, increased suggests addition by 1. So here's our inequality, and let's solve it similar way as before. You may want to finish this on your own and then double check with my answer. So we are subtracting 1 from all three sides. We get 1 smaller than 2x smaller than 7, and finally we divide by 2. So x is enclosed by 1/2 from the left and 7/2 from the right. On the number line, if this is my 1/2, no equation, hollow dot, and that's 7/2, again hollow dot, the solution set is composed of all numbers that are in between. Final answer in interval notation: any x that belongs to the interval 1/2 to 7/2 is a solution. Next example. Again, first try it on your own. If 5 is subtracted from a number, then the result is at least 7. The phrase "at least" indicates inequality. At least means more or equal. So whatever phrase we have here, 5 subtracted from a number, it will be more or equal 7. Okay, let's start building this inequality. Bigger equals 7. What is bigger equals 7? 5 subtracted from a number. So first I have to have a number and then subtract 5. 5 subtracted from a number is at least 7 or more. So this is a single inequality. It's enough to add 5 to both sides and we have our solution. 7 plus 5 is 12. As usual, we can draw it on the number line. If 12 is somewhere there, it will be marked by a cover dot because of the equation. Everything that is higher than that will be our solution. So the answer is x can be anything from 12, including 12, until infinity. Let's try some word problems that involve inequalities. After a serious automobile accident, most insurance companies will replace the damaged car with a new one if repair costs exceed 80% of the Blue Book value of the car. John's car recently sustained $9,200 worth of damage but was not replaced. If it was not replaced, that means the repair costs did not exceed 80% of the Blue Book value. What can we say about the Blue Book value of his car? Well, since the question asks us about the Blue Book value, then we need to introduce a variable for it. Let B represents the Blue Book value. Then what do we know about the B value? Since John's car was not replaced, then the cost of repair, $9,200, did not exceed 80% of the B value. So let's try to write it down. The cost $9,200 did not exceed. That means it's not bigger, therefore is smaller or equal. 80% corresponds to 0.8. Of corresponds to multiplication, and Blue Book value is our B. So 9,200 is smaller or equal than 0.8b. Okay, that was the hardest part of the problem. Now to solve it, it's not so difficult. We know how. Let's divide by 0.8, and the Blue Book value must be bigger equal than 9,200 divided by 0.8, which turned out to be 11,500. So the Blue Book value of the car must have been at least 11,500. Let's give the answer. The Blue Book value was at least $11,500. Let's see one more example. Tony can be paid in one of two ways. according to plan A or according to plan B. Plan A says he can get a salary of $400 per month plus commission of 8% of the gross sales. According to plan B, he can get $610 per month plus a commission of just 5% of gross sales. For what amount of gross sales should Tony select plan A? Well, Tony would select plan A if plan A would give him more money. So, since we don't know the gross sales, let's introduce a variable. Let S represent the gross sales. Then we need to figure out the expression in terms of gross sales, meaning S, of his pay according to plan A. So, according to plan A, he will be paid $400 plus a commission of 8% of gross sales. So 8% is 0.08 and the amount of gross sales is S, 0.08 S. Okay, let's see how much money would he get according to plan B. He would get $610 without doing anything, but on the top of it, he would get 5% of gross sales, so 0.05 of S. Now, we want to know when Tony will select plan A. That suggests that plan A should give him more money. Therefore, we place this inequality. It's bigger. Okay, let's solve it. We need to collect all s's to one side. Let's put it to the left. It will be 0.08 minus 0.05, so it's 0.03s, bigger than, and 610 minus 400 is 210. Last step, we divide by 0.03. We end up with s bigger than 210 over 0.03, which gives us $7,000. Okay, we're ready to give the final answer. For what amount of gross sales should Tony select plan A? Tony should select plan A only if he expects his gross sale to be over $7,000. For gross sales over $7,000. Exactly at $7,000, it wouldn't matter which plan he will choose. If he expects his gross sales to be lower than $7,000, plan B would be better for him. But if he expects the gross sales to be more than $7,000, then plan A would be beneficial for him.